Morning, everyone. So again, it's Sir Capistrano. So for today class, we will be talking about, uh, or for this video, we will be actually talking about the extension of our discussion last time regarding atoms, molecules, and ions. Wherein we will continue on discussing some other chemical nomenclature. So these are just some special namings that are not included in our discussion last time, wherein we have learned how we can name other compounds, specifically ionic compounds and molecular compounds, wherein we already presented this some sort of a flow chart last time regarding on how we can name those ionic and molecular compounds. So for today, we will be actually discussing some special naming wherein we will be talking about the nomenclature of acids, oxoacids, bases, hydrates, and other organic compounds. So first off, let's have for an acid. So by definition, an acid can be defined as a substance that yields hydrogen ions, which is H plus, when dissolved in water. So basically, when we talk about acids, these are just combinations of an ion and also a hydrogen atom ions. So here are some examples. For example, we have HCl gas. So if that HCl gas is dissolved in water, we will have first we will have the pure substance hydrogen chloride, but whenever it is aqueous, meaning to say dissolved in water, uh, it will yield the hydronium ion, which is actually just equivalent to hydrogen ions, that is H3O plus, and we will also have the chlorine ion. Basically, from since we have their water and we have their our hydrogen chloride, due to due to being dissolved in water, there is some sort or a process called dissociation, wherein hydrogen chloride will produce hydrogen ion and an ion, wherein that H plus will join the water. Okay, therefore forming what we call hydronium ion. In that, due to that dissolution, we will have what we call hydrochloric acid. But we are not actually concerned regarding the process on how that happened. We will be just pointing out here that when we talk about acids, these are pure substances containing hydrogen that when dissolved in water will produce hydronium ion or hydrogen ions and the anion or the corresponding anion. And for naming of acids, we just need to specify the hydro, which means that that is the hydrogen, and chloric, which is chlorine. So we just added IC in the naming, therefore having hydrochloric acid. So here we have here some examples of other anion and their corresponding acids. So we have here for fluorine or fluoride ion, we have here hydrofluoric acid. Again, hydro, then fluorine. We just remove the INE and replace it with IC. Therefore, we have there hydrofluoric acid. Also, we have here our hydrochloric acid, hydrogen chlorine, hydrobromic acid, which is hydrogen bromine. Then we have here iodine or iodide ion, an ion. So we will have here hydroiodic acid, and we have here cyanide. So we have here hydrocyanic acid, and lastly we have here sulfide. So we will have here hydrosulfuric acid. So in that class, these are not all of the examples of acids. There's a lot of other type of acids that we may encounter around us. But for now, these are just the common examples of our acids. So in talking about acids, we will not be talking about acids when na hindi natin mababanggit ang ating oxoacids. By oxoacids, these are acids that contains hydrogen, oxygen, and other elements. So, for the acid part, that will be our hydrogen ions, and for oxo, we will have there our oxygen. So, some examples of oxoacids are nitric acid. So, we have here our hydrogen, our oxygen, and also we have here our nitrogen. So also we have here carbonic acid. We also have here phosphoric acid. These are just some common examples of our oxoacids. So basically, if we encounter an acid that has hydrogen and oxygen, we call them oxoacids. And syempre, katulad ng mga unang acids na pinag-usapan natin, these acids are actually pure substances when they are not dissolved in water. So, they only became or become uh, acids whenever they are dissolved in water or in aqueous form. So, keep that in mind. All acids and bases exist as acids or bases when they are in aqueous form. So, in naming oxoacids, we actually follow what we call this system, wherein we name the oxoacids and the oxoanions. Wherein for the oxoacids, we refer it as this. So usually we assign a reference ic acid, and depending on the numbers of their oxygen, there is a change on how we call them. Usually the reference number of oxygen atoms in an oxoacid is 3. So if that oxoacid has less oxygen, instead of using IC, we will use OUS or OUS acid. Then if we deduct another oxygen, we will have their hypo something OUS acid. And if we have additional oxygen for our ic oxoacid, that will be per something ic acid. So that is paired with their oxoan ions, wherein if we remove all H ions, the pairic will be pairate, ic will be 8, us will be 8, and hypoos will be hypoite. So here are some examples or rules on how we follow that. So when all H ions are removed from ic acids, the anion name ends with it. And when all H ions are removed from the us acid, the anion names end with ite. And the names of an ion in which one or more, but not all hydrogen ions have been removed, must indicate the number of H ions present. For example, if we have our phosphate, here are some examples of our anion, oxoanions. So we have here dihydrogen phosphate. So if we convert this to its oxoacid uh, phase, that will be H, no, it should be H2 PO4H or H3PO4. So that will be 4. So that will be per phosphoric acid. Okay. So as you can see here, the 8 will become 8. And since not all of the hydrogen ions are removed, we have here two hydrogen ions or two hydrogen atoms. We have here dihydrogen. So same. So if we remove two hydrogen atoms in our perphosphoric acid or phosphoric phosphoric acid, we will have here hydrogen phosphate. And if we remove all of the hydrogen atoms, we will have here phosphate. Okay. So same goes for the height. So if we have, let's say, what can be an example of this? Height. So let's have, if we have here, hmm, we'll just discuss those examples whenever we encounter them. So for the names of the oxoacids and oxoions that contains chlorine, we have here, this will be our reference point, our chloric acid. If we add another, so as you may see here, we have here three oxygen. If we have, or we added one oxygen atom, that will be perchloric acid. And its counterpart, an ion, will be perchlorate. So we have here, if from 3, we remove another oxygen atom, that will be chlorous acid. And its an ion is named chloride. And for the hypochlorous acid, that will be hypochlorite. So you may be thinking, Sir, bakit kailangan nating alamin yung pangalan ng anion nila? So as mentioned in the discussion of acid, whenever this or any of this pure substance is, say, dissolved in water, again, we will have here the dissociation of our hydrogen atom. Meaning to say, if perchloric or our perchlorate is actually dissolved in water, this hydrogen atom will be removed from that ion, therefore producing what we call an oxoion. That's why we have a system on how we name our oxoanions. Okay? And if we are talking about acids, of course, we need to talk about bases. Okay? So, by bases, this is just the counterpart of acid. Uh, a base can be defined as a substance that yields hydroxide ions when dissolved in water. Again, let's underline that. Again, a base can be defined as a substance that yield the hydroxide ions when dissolved in water. So, whenever these substances or these bases are not dissolved in water, they are actually considered as pure substances. So they become bases, like the acid, whenever they are dissolved in water. So some examples of those pure substances that became bases whenever dissolved in water, we have here our sodium hydroxide. We also have here potassium hydroxide, and we have here barium hydroxide. So for the naming, we just need to mention the metal part of the bases. Then mention the hydroxide part of the bases. So just like our acids, whenever they are dissolved in water, our our pure substances actually undergoes what we call dissociation again, or you know, the ions are separated from each other due to its aqueous form. Therefore, for our sodium hydroxide, it will form our Na plus ion, cation, and also we have here an OH, an ion. Same goes for potassium hydroxide. We will have here our K plus and OH minus. And for barium hydroxide, we will have here barium, which is 2 plus, and we will have here two hydroxide ions. Okay, so that is how bases happens. So for the next special nomenclature, we have here hydrates. So hydrates are just compounds, may it be, but usually it is ionic compounds that have specific numbers of water molecules attached to them. So basically, it's just like this. We have here barium chloride. Barium chloride, as you may have remember, is an ionic compound, and it is paired with two uh, water molecules. So in naming this, we just mention the, the ionic name, which is barium chloride, and then we add our dihydrate. By dihydrate, that will be two water molecules. So if we have here lithium chloride, then paired with one molecule of water, that will be lithium chloride hydrate or monohydrate, sorry. So you need to mention the mono part of the hydrate. And next, we have here magnesium sulfate with seven water molecules, meaning to say we will have here magnesium sulfate heptahydrate, hepta for seven. So we also have here this compound, which is strontium nitrate tetrahydrate. Right? So what is the difference between the hydrates? So we have here copper sulfate penta hydrate, and compare that to copper sulfate, and you may notice that the hydrate part assume a more uh, crystalline appearance, while the ionic form or the salt form of copper sulfate actually looks like a powder. So that is the difference between hydrates and their ionic compound counterparts. Okay. So here are some other common and systematic names of some compounds. So we have their just the common household materials that you may find in your house. So we have here water, ammonia, dry ice, not so common, table salt, laughing gas, which is used in dental clinics, but rarely nowadays. We also have marble, chalk, and limestone, which is just calcium carbonate. We have quicklime or calcium oxide, slacklime, calcium hydroxide. We have here baking soda, which is actually NaHCO3, which is sodium hydrogen carbonate. We also have the washing soda, which is actually hydrate. So we have here sodium carbonate decahydrate. We also have Epsom salt or the magnesium sulfate heptahydrate. We also have milk of magnesia or magnesium hydroxide. We also have gypsum, which is calcium sulfate dihydrate. Okay, so I think this is the last part or the last special series of names. So in your next course after this Chem Zero, you will actually have organic chemistry. So in organic chemistry, by definition, it is a branch of chemistry that deals with carbon compounds. Meaning to say, these are compounds having carbon atoms. So here are some examples of carbon compounds in organic chemistry, which are actually characterized using functional groups. So we have here this one first, and as you may notice here, this is our carbon compound, and we also have there our OH. So this OH here is actually what we call the functional group. So what is the sense of the functional group? Let's wait until we have here another example. As you may see here, these compounds actually looks somehow the same. They both have the CH3, this one CH3 group, and also they only differ in this branch of the chemical compound or of the compound. For the first part, we have here the OH, and here we have here the amine. So meaning to say, we have here this name, metylalamine. So as you may notice, they both have the name meta, met. So they both have the name met in their names. So what is the significance of that? You will see later on. So also we have here another compound that is somehow related to this too. So we have here this CH3 group, and we have here the COOH. So that is the difference between those three. So we have here the OH, we have here the NH2, and we have here the COOH. So this is acetic acid. So in here, as you may have noticed, in organic chemistry, there is another system that we will be tackling during your organic chemistry, wherein the name of each compound or carbon compounds depends on the type of the functional groups it is attached to. So in that, the basics actually, when in organic chemistry, the names of the compound usually based on the number of the carbon groups or the carbon in the main chain group. So we will be talking about that later on next semester. So in that, here are some examples of some straight chain alkanes. So as you may see here, from the mono, di, tri, and something, organic chemistry uses another system wherein we will have here our met, et, prop, but, pent, hex, hep, oct, non, and dec. So we will be talking more about that later on your organic chemistry. But in that, it just shows that there is another system on how we can name carbon compounds. So if we see, for example, CH4, we cannot name that as carbon tetrahydride, for or for ethane, it cannot be named as dicarbon hexahydrogen. Okay, so there is another system on naming carbon compounds, which we will be talking about next semester. And for now, that is all for today. So today we actually talked about the special or the other ways or the other chemical nomenclature of different types of compounds or chemicals. Wherein today we have talked about naming acids, naming oxoacids, naming bases, naming hydrates, and also naming oxoanions and also our organic compounds. In that ends this video. Bye.